Create a Tic-Tac-Toe Python Game Engine with an AI player. When you were young, you may have learned to play tic-tac-toe, known by some as noughts and crosses. The game remains fun and challenging until you get a bit older. Then you learn to program and discover the joy of coding a virtual version of this two-player game. As an adult, you may still appreciate the simplicity of the game by using Python to create an opponent with artificial intelligence. In this course, you'll build an extensible game engine with an unbeatable computer player that uses the minimax algorithm to play tic-tac-toe. Along the way, you'll dive into immutable class design, generic plugin architecture, and modern Python code practices and patterns. In this course, you'll learn how to create a reusable Python library with the Tic-Tac-Toe Game Engine, model the domain of tic-tac-toe following Pythonic code style, implement artificial players, including one based on the minimax algorithm, and build a text-based console front-end for the game with a human player. This is an advanced course touching on a wide range of Python concepts that you should be comfortable with in order to complete the course smoothly. Remember that Real Python has tutorials and courses on all of these subjects if you feel there are any areas that you need to work on. But one of the best ways to learn something is to throw yourself into it and learn as you go. You can always dive deeper into them after this course if you feel you want to know more on any of these areas. The project that you're going to build relies solely on Python's standard library and has no external dependencies. It was recorded using Python 3.12, but you'll need at least Python 3.11 or later to take advantage of the latest syntax and features that are leveraged in this course. Lastly, you should know the rules of the game that you'll be implementing. The classic tic-tac-toe is played on a 3x3 grid of cells or squares where each player places their mark, an X or an O, in an empty cell. The first player to place 3 of their marks in a row horizontally, vertically, or diagonally wins the game. So now that you know what you need and what you'll be building, let's get started by taking a look at the finished game in action. Demo and project overview. By the end of this course, you'll have a highly reusable and extensible Python library with an abstract game engine for tic-tac-toe. It will encapsulate universal game rules and computer players, including one that never loses due to bare-bones artificial intelligence support. In addition, you'll create a sample console front-end that builds on top of your library and implements a text-based interactive tic-tac-toe game running in the terminal. On screen, you can see actual gameplay between 2 players. Generally, you can mix and choose the players from among a human player, a dummy computer player making moves at random, and a smart computer player sticking to the optimal strategy. You can also specify which player should make the first move, increasing their chances of winning or tying. Later on, you'll be able to adapt your generic tic-tac-toe library for different platforms, such as a Windows desktop environment or a web browser. While you'll only follow instructions on building a console application in this course, you can find Tic-Tac-Toe and PyScript front-end examples in the course materials. These front-ends aren't covered here because implementing them requires considerable familiarity with threading, async I/O, and queues in Python, which is beyond the scope of this course. But feel free to study and play around with the sample code on your own. The Tic-Tac-Toe front-end is a streamlined version of the same game that's described in a separate tutorial, which only serves as a demonstration of the library in a desktop environment. Unlike the original, it doesn't look as slick, nor does it allow you to restart the game easily. However, it adds the option to play against the computer or another human player if you want to. The PyScript front-end lets you or your friends play the game in a web browser even when they don't have Python installed on their computer, which is a notable benefit. If you're adventurous and know a little bit of PyScript or JavaScript, then you could extend this front-end by adding the ability to play online with another human player through the network. It's worth noting that each of the 3 front-ends demonstrated in this section merely implement a different presentation layer for the same Python library, which provides the underlying game logic and players. There's no unnecessary redundancy or code duplication across them, thanks to the clear separation of concerns and other programming principles that you'll practice in this course. The project that you're going to build consists of two high-level components as seen on screen. The first component is an abstract Tic-Tac-Toe Python library, which is agnostic about the possible ways of presenting the game to the user in a graphical form. Instead, it contains the core logic of the game and two artificial players. But the library can't stand on its own, so you're also going to create a sample front-end to collect user input from the keyboard and visualize the game in the console using plain text. You'll start by implementing the low-level details of the Tic-Tac-Toe library, and then you'll use those to implement a higher-level game front-end in a bottom-up fashion. When you finish this course, the complete file structure resulting will look as seen on screen. The front-ends folder is meant to house one or more concrete game implementations, such as your text-based console version. Library is the home folder for the game library. You can think of both top-level folders as related but separate projects. Note that the console front-end contains the dundomain.py file, making it a runnable Python package that you'll be able to invoke from the command line using the -m option. Once you've completed the project or downloaded the completed code from the course materials, from the front-ends folder you'll be able to start the game with the command seen on screen. Remember that Python must be able to find the Tic-Tac-Toe library, which your front-end depends on the module search path. The best practice for ensuring this is by creating and activating a virtual environment and installing the library with pip. You'll find detailed instructions on how to do this in the README file in the supporting materials. The Tic-Tac-Toe library is a Python package named tic_tac_toe consisting of two sub-packages. Tic-Tac-Toe Game is a scaffolding designed to be extended by the front ends, and Tic-Tac-Toe Logic is the building blocks of the Tic-Tac-Toe game. You'll dive deeper into each of them soon. The pyproject.toml file contains the metadata necessary for building and packaging the library. To install the downloaded library or the finished code that you'll build in this course into an active virtual environment, try the command seen on screen. During development, you can make an editable install using pip with the E or editable flag to mount the library source code instead of the built package in your virtual environment. This will prevent you from having to repeat the installation after making changes to the library to reflect them in your front end. In the next part of the course, you'll get started on creating the game by looking at modeling the game domain. Model the Tic-Tac-Toe game domain. In this step, you'll identify the parts that make up the Tic-Tac-Toe game and implement them using an object-oriented approach. By modeling the domain of the game with immutable objects, you'll end up with modular and composable code that's easier to test, maintain, debug, and reason about, amongst several other advantages. To get started, open the code editor of your choice, such as Visual Studio Code or PyCharm, and create a new project called Tic-Tac-Toe, which will also become the name of your project folder. Many modern code editors will give you the option to create a virtual environment for your project automatically, so if you want to, you can do that. But if your editor doesn't, then you can make the virtual environment manually. On macOS and Linux, this will create a Tic-Tac-Toe folder and move into it. Then it will create a virtual environment in the VN folder inside Tic-Tac-Toe and activate it. If you're on Windows using Windows Terminal, then the commands are slightly different. Next, scaffold the basic structure of files and folders in your new project, remembering to use underscores instead of dashes for the Python package in the src subfolder. This skeleton of folders and files is available in the course materials if you don't want to create everything manually. All of the files in the tree seen on screen should be empty at this point. You'll successively fill them with content and add more files as you go through the course. Start out by editing pyproject.toml. You can enter the minimal packaging configuration seen on screen into it. You specify the required build tools, which Python will download and install if necessary, along with some metadata for the project. Adding the pyproject.toml file to the library lets you build and install it as a Python package into the active virtual environment. Open a terminal with a virtual environment activated and enter this command to install the Tic-Tac-Toe library in the editable mode. Even though there's no Python code in the library yet, installing it now with the editable flag will let the Python interpreter import the functions and classes that you'll be adding shortly straight from your project. Otherwise, every time you made a change in your source code and wanted to test it, you'd have to remember to build and install the library into the virtual environment again. Now you have a general structure for the project, you can start implementing some code. By the end of this step, you'll have all the essential pieces of a tic-tac-toe game in place, including the game logic and state validation, so you'll be ready to combine them in an abstract game engine. At the start of the game, each tic-tac-toe player gets assigned one of two symbols, either cross, X, or naught, O, which they use to mark locations on the game board. Since there are only two symbols belonging to a fixed set of discrete values, you can define them with an enumerated type or enum. Using enums is preferable over constants due to their enhanced type safety, common namespace, and programmatic access to their members. Create a new Python module called models in the Tic-Tac-Toe logic package. You'll use this file to define Tic-Tac-Toe domain model objects. Now, import the enum module from Python standard library and define a new data type in your models. The two singleton instances of the mark class, enum members cross and naught, represent the player's symbols. They're defined as an extension of enum string enum, which was added to the standard library in Python 3.11. Members of enum string enum are strings, which means that you can use them almost anywhere that a regular string is expected. Once you assign a given mark to the first player, the second player must be assigned the only remaining and unassigned mark. Because enums are glorified classes, you're free to put ordinary methods and properties into them. For example, you can define a property of a mark member that will return the other member. The body of the property is a single line of code that uses a conditional expression to determine the correct mark. The quotation marks around the return type in the property's signature are mandatory to make a forward declaration and avoid an error due to an unresolved name. After all, you claim to return a mark which hasn't been fully defined yet. Alternatively, you can postpone the evaluation of annotations until after they've been defined. Adding the special dunder future import, which must appear at the beginning of the file, enables lazy evaluation of type hints. You'll use this pattern later to avoid the circular reference problem when importing cross-referencing modules. You can see a few practical uses of the mark enum in the REPL session seen on screen. You can refer to a mark by its symbolic name literal, its string name, or by its value. You can get the other mark its name, and its value. You can compare it to a string, use it as if it were a string, and iterate over the available marks. You now have a way to represent the available markings that players will leave on the board to advance the game. In the next section of the course, you'll implement an abstract game board with well-defined locations for those markings. Represent the square grid of cells. While some people play variants of tic-tac-toe with a different number of players or different sizes of grids, you'll stick with the most basic and classic rules. You may recall that the classic game's board is represented by a 3x3 grid of cells. Each cell can be empty or marked with either a cross or a naught. Because you represent marks with a single character, you can implement the grid using a string of precisely 9 characters corresponding to the cells. A cell can be empty, in which case you'll fill it with the space character, or it can contain the player's mark. In this course, you'll store the grid in row major order by concatenating the rows from top to bottom. For example, with this representation, you could express the 3 gameplays demonstrated before with the string literals seen on screen. To better visualize them, you can create this short function in a REPL session. The function takes a string of cells as an argument and prints it out onto the screen in the form of 3 separate rows carved out with the slice operator from the input string. While using strings to represent the grid of cells is straightforward, it falls short in terms of validating its shape and content. Other than that, plain strings can't provide some extra grid-specific properties that you may be interested in. For these reasons, you'll create a new grid data type on top of a string wrapped in an attribute. You define grid as a frozen data class to make its instance immutable, so once you create a grid object, you won't be able to alter its cells. This may sound limiting and wasteful at first, because you'll be forced to make many instances of the grid class instead of reusing just one object. However, the benefits of immutable objects, including fault tolerance and improved code readability, far outweigh the costs in modern computers. By default, when you don't specify any value for the cells attribute, it will assume a string of exactly 9 spaces to reflect an empty grid. However, you can still initialize the grid with the wrong value for cells, ultimately crashing the program. You can prevent this by allowing your objects only to exist if they're in a valid state. Otherwise, they won't be created at all, following the fail fast and always valid domain model principles. Data classes take control of object initialization, but they also let you run a post-initialization hook to set derived properties based on the values of other fields, for example. You'll take advantage of this mechanism to perform cell validation and potentially discard invalid strings before instantiating a grid object. The dunder post init method uses a regular expression to check whether the given value of the cells attribute is exactly 9 characters long and contains only the expected characters X, O, or space. There are other ways to validate strings, but regular expressions are very compact and will remain consistent with the future validation rules you'll add later on. If the cells attribute does not pass the test, then a value error is raised. Note that the grid is only responsible for validating the syntactical correctness of a string of cells, but it doesn't understand the higher level rules of the game. You'll implement the validation of a particular cell combination semantics elsewhere once you gain additional context. At this point, you can add a few extra properties to your grid class which will become handy when determining the state of the game. These three properties return the current number of crosses, noughts, and empty cells respectively. Because your data class is immutable, its state will never change, so you can cache the computed property values with the help of the cached property decorator from the functools module. This will ensure that their code will run at most once, no matter how many times you access the properties, for example during validation. On screen you can see the grid class in action, showing some of its features. You can create an empty grid, or one with a particular cell combination. The grid creation process will check if the grid has too few cells, or the wrong characters. You can get the count of X's, O's, or empty cells. Using Python code, you've modeled a 3x3 grid of cells which can contain a particular combination of players' marks. Now it's time to model the player's move so that artificial intelligence can evaluate and choose the best option, and you'll be doing that in the next video. Take a snapshot of the player's move. An object representing the player's move in tic-tac-toe should primarily answer two questions. Firstly, the player's mark. What mark did the player place? Secondly, the mark's location. Where was it placed? However, in order to have the complete picture, one must also know about the state of the game before making a move. After all, it could be a good or bad move depending on the current situation. You may also find it convenient to have the resulting state of the game at hand so you can assign it a score. By simulating that move, you'll be able to compare it with other possible moves. A move object can't validate itself without knowing some of the game details, such as the starting player's mark, which aren't available to it. You'll check whether a given move is valid, along with validating a specific grid cell combination in a class responsible for managing the game's state. Based on these thoughts, you can add another immutable data class to your models. Ignore the two forward declarations of the GameState class for the moment, as you'll define it next. Your new class is strictly a data transfer object whose main purpose is to carry data, as it doesn't provide any behavior through methods or dynamically computed properties. Objects of the move class consist of the mark identifying the player who made a move, a numeric 0 based indexing of the string of cells, and the two states before and after making a move. The move class will be instantiated, populated with values, and manipulated by the missing GameState class. Without it, you won't be able to correctly create the move objects yourself, so it's time to fix that now. A tic-tac-toe game can be in one of several states, including three possible outcomes. The game hasn't started yet, the game is still going on, the game is finished in a tie, the game is finished with player X winning, and the game is finished with player O winning. You can determine the current state of a game of tic-tac-toe based on two parameters: the combination of the cells in the grid, and the mark of the starting player. Without knowing who started the game, you won't be able to tell whose turn it is now and whether the given move is valid. Ultimately, you can't properly assess the situation so that the artificial intelligence can make the right decision. To fix that, begin by specifying the game state as another immutable data class consisting of the grid of cells and the starting player's mark. By convention, the player who marks the cells with crosses starts the game, hence the default value of mark X for the starting player's mark. However, you can change it according to your preference by supplying a different value at runtime. Now add a cached property returning the mark of the player who should make the next move. The current player's mark will be the same as the starting player's mark when the grid is empty or when both players have marked an equal number of cells. In practice, you only need to check the latter condition because a blank grid implies that both players have 0 marks on the grid. To determine the other player's mark, you can take advantage of the other property in the mark enum. Next up, you'll add some properties for evaluating the current state of the game. For example, you can tell that the game hasn't started yet when a grid is blank or contains exactly 9 empty cells. This is where the grid's properties come in handy. Conversely, you can conclude that the game has finished when there's a clear winner or there's a tie. The winner property that you'll implement in a bit will return a mark instance or none, whereas the tie property will be a Boolean value. A tie is when neither player has won, which means there's no winner, and all of the squares are filled, leaving no empty cells. Both the game over and tie properties rely on the winner property, which they delegate to. Finding a winner is slightly more difficult though. You can, for example, try to match the current grid of cells against a predefined collection of winning patterns with regular expressions. There are 8 winning patterns: 3 horizontal lines, 3 vertical lines, and 2 diagonal lines. You define them using templates resembling regular expressions. The templates contain question mark placeholders for the concrete player's mark. You iterate over those templates and replace the question marks with both players' marks to synthesize 2 regular expressions per pattern, one containing each player's mark. When the cells match a winning pattern, then you return the corresponding mark, the mark of the winner. Otherwise, you return none. Knowing the winner is one thing, but you may also want to know the matched winning cells to differentiate them visually. In this case, you can add a similar property. This will use a list comprehension to return a list of integer indices of the winning cells. Now you may be concerned about having a bit of code duplication here between winner and winning cells, which violates the don't repeat yourself dry principle. Here that's okay. The Zen of Python says that practicality beats purity, and in this case extracting the common denominator would provide little value but make the code much less readable. It usually makes sense to start thinking about refactoring your code when there are at least 3 instances of a duplicated code fragment, because then there's a high chance that you'll need to reuse the same piece of code even more. Game state is starting to look pretty good. It can correctly recognize all possible game states, but it does lack proper validation, making it prone to runtime errors. In the next video, you'll rectify that by codifying and enforcing a few tic-tac-toe rules. Introduce a separate validation layer. As with the grid, creating an instance of the GameState class should fail when the supplied combination of cells and the starting player's mark don't make sense. For example, it's currently possible to create an invalid game state that doesn't reflect genuine gameplay. And you can test this yourself. Start an interactive Python interpreter session in the virtual environment where you'd previously installed your library, and run the code seen on screen. Here you initialize a new game state using a grid comprising a syntactically correct string with the right characters and length. But such a cell combination is semantically incorrect because one player isn't allowed to fill the entire grid with their mark. Because validating the game state is relatively involved, implementing it in the domain model would violate the single responsibility principle and make your code less readable. Validation belongs to a separate layer in your architecture, so you should keep the domain model and its validation logic in two different Python modules without mixing their code. Go ahead and create two new files in your project, exceptions.py and validators.py. You'll store various helper functions in validators.py and a few exception classes in the exceptions.py file to decouple game state validation from the model. For improved code consistency, you can extract the grid validation that you defined earlier in the post-init method and move it into the newly created Python module and wrap it in a new function. Note that you replace self.cells with grid.cells because you're now referring to a grid instance through the function's argument. After extracting the grid validation logic, you should update the corresponding part in the grid model by delegating the validation to an appropriate abstraction. First, you import the new helper function. And then you call it in the grid's post-initialization hook, which now uses a higher level vocabulary to communicate its intent. Previously, some low-level details, such as the use of regular expressions, were leaking into the model, and it wasn't immediately clear what the dunder post-init method does. Unfortunately, this change now creates the notorious circular reference problem between the model and validator layers, which mutually depend on each other. When you try to import grid, you'll get the error seen on screen. This is because Python reads the source code from top to bottom. As soon as it encounters an import statement, it will jump to the imported file and start reading it. But in this case, the imported validators module wants to import the models module, which hasn't been fully processed yet. This is a very common problem in Python when you start using type hints. The only reason you'd need to import models is because of a type hint in your validating function. You could get away without the import statement by surrounding the type hint with quotes to make a forward declaration as seen earlier on in the course. But you'll follow a different idiom this time. You can combine the postponed evaluation of annotations with a special type checking constant. You import grid conditionally. The type checking constant is false at runtime, but third-party tools such as MyPy will pretend it's true when performing static type checking to allow the import statement to run. However, because you no longer import the required type at runtime, you must now use forward declarations or take advantage of from dunder future import annotations, which will implicitly turn annotations into string literals. Note that the dunder future import was originally intended to make the migration from Python 2 to Python 3 more seamless. Today you can use it to enable various language features planned for future releases. Once a feature becomes part of the standard Python distribution and you don't need to support older language versions, you can remove the import. You can read more about this behavior at the link to the Python documentation seen on screen. The import statement that previously generated an error now works correctly. With all of this plumbing in place, you're finally ready to constrain the game state to comply with the tic-tac-toe rules. In the next section of the course, you'll add a few game state validation functions to the new Validators module. Discard incorrect game states. In order to reject invalid game states, you'll implement a familiar post-initialization hook in your GameState class that delegates the processing to another function. The validating function, validateGameState, receives an instance of the game state, which in turn contains the grid cells and the starting player. You'll use this information, but first you'll split the validation into a few smaller and more focused stages by delegating bits of the state further down in your Validators module. Your new helper function serves as an entry point to the game state validation by calling a few subsequent functions that you'll define presently. To prevent instantiating a game state with an incorrect number of players' marks in the grid, such as the one that you stumbled on earlier on, you must take the proportion of noughts to crosses into account. At any time, the number of marks left by one player must be either the same or greater by exactly 1 compared to the number of marks left by the other player. Initially, there are no marks, so the number of X's and O's is equal to 0. When the first player makes a move, they'll have 1 more mark than their opponent. But as soon as the other player makes their move, the proportion evens out again, and so on. To signal an invalid state, you raise a custom exception defined in another module. It's customary to have empty classes extend the built-in exception type in Python without specifying any methods or attributes in them. Such classes exist solely for their names, which convey enough information about the error that occurred at runtime. Notice that you don't need to use the pass statement or the ellipsis literal as a class body placeholder if you use a docstring, which can provide additional information. Another game state inconsistency related to the number of marks left on the grid has to do with the starting player's mark, which may be wrong. The player who left more marks on the grid is guaranteed to be the starting player. If not, then you know something must have gone wrong. Because of the way mark was defined, you can directly compare the starting player's mark to a string literal. Finally, there can be only one winner, and depending on who started the game, the ratio of X's and O's left on the grid will be different. A starting player has an advantage, so when they win, they'll have left more marks than their opponent. Conversely, the second player is at a disadvantage, so they can only win the game by making an equal number of moves as the starting player. You're almost done with encapsulating the tic-tac-toe game's rules in Python code, but there's still one more important piece missing. In the next video, you'll write code to systematically produce new game states by simulating players' moves. Simulate moves by producing new game states. The last property that you'll add to your GameState class is a fixed list of possible moves, which you can find by filling the remaining empty cells in the grid with the current player's mark. If the game is not over, you identify the locations of empty cells using a regular expression, and then make a move to each of those cells. Making a move creates a new move object, which you append to the list without mutating the game state. If the game is over, you return an empty list of moves. This is how you construct a move object. A move isn't allowed if a target cell is already occupied by either your or your opponent's mark, in which case you raise an invalid move exception. On the other hand, if the cell is empty, then you take a snapshot of the current player's mark, the target cell's index, and the current game state, while synthesizing the following state. Don't forget to define the new exception type that you imported. And that's it. You've now got a solid domain model of the tic-tac-toe game, which you can use to build interactive games for various front ends. The model encapsulates the game's rules and enforces its constraints. In the next section of the course, you'll build an abstract game engine and your first artificial player. Scaffold a generic tic-tac-toe game engine. At this point, you should have all the domain models defined for your tic-tac-toe library. Now it's time to build a game engine that will take advantage of these model classes to facilitate tic-tac-toe gameplay. Go ahead and create 3 more Python modules inside the tic-tac-toe game package as seen on screen. The engine module is the centerpiece of the virtual gameplay, where you'll implement the game's main loop. You'll define abstract interfaces that the game engine uses, along with a sample computer player in the Players and Renderers module. By the end of this step, you'll be set to write a tangible front end for the tic-tac-toe library. At the very minimum, to play a tic-tac-toe game, you need to have 2 players, something to draw on, and a set of rules to follow. Fortunately, you can express these elements as immutable data classes, which take advantage of the existing domain model from your library. First, create the Tic-Tac-Toe class in the Engine module. Both player and renderer will be implemented in the following sections as Python's abstract base classes. These only describe the high-level interface for the game engine. They'll eventually get replaced with concrete classes, some of which may come from an externally defined front end. The player will know what move to make, and the renderer will be responsible for visualizing the grid. To play the game, you must decide which player should make the first move, or you can assume the default one, which is the player with crosses. You should also begin with a blank grid of cells and an initial game state. The engine requests that the renderer update the view and then uses a pull strategy to advance the game by asking both players to make their moves in alternating rounds. These steps are repeated in an infinite loop until the game is over. Game state only knows about the current player's mark, which can be either X or O, but it doesn't know about the specific player objects that were assigned those marks. Therefore, you need to map the current mark to a player object using this helper method. Here, you compare enum members by their identities using Python's is operator. If the current player's mark determined by the game state is the same as the mark assigned to the first player, then that's the player who should be making the next move. Both players supplied to the tic-tac-toe object should have opposite marks. Otherwise, you wouldn't be able to play the game without violating the rules. So it's reasonable to validate the player's marks when instantiating the tic-tac-toe class. You add a post-initialization hook to the data class and call another validation function that you have to add into your Validators module. You use the identity comparison again to check both players' marks and prevent the game from starting when both players use the same mark. There's one more thing that can go wrong. Because it's up to the players, including human players, to decide what move they make, their choice could be invalid. Currently, the tic-tac-toe class catches the invalid move exception, but it doesn't do anything useful with it, other than ignore such a move and ask the player to make a different choice. It would probably help to let the front end handle errors by, for example, showing a suitable message. To let the front end decide how to take care of an invalid move, you expose a hook in the class by introducing an optional error handler callback, which will receive the exception. You define the callback's type using a type alias, making its type declaration more concise. The tic-tac-toe game will trigger this callback in case of an invalid move, as long as you provide the error handler. Having implemented an abstract tic-tac-toe game engine, you can proceed to code an artificial player. In the next section of the course, you'll define a generic player interface and implement it with a sample computer player that makes moves at random. Let the computer pick a random move. First, define an abstract player, which will be the base class for concrete players to extend. An abstract class is one that you can't instantiate because its objects wouldn't stand on their own. Its only purpose is to provide the skeleton for concrete subclasses. You can mark a class as abstract in Python by setting its meta class to ABC, ABC meta, or extending the ABC, ABC ancestor. Using the meta class argument instead of extending the base class is slightly more flexible, as it doesn't affect your inheritance hierarchy. This is less important in languages like Python, which support multiple inheritance. But as a rule of thumb, you should favor composition over inheritance wherever possible. The player gets assigned a mark instance that they'll be using during the game. The player also exposes a public method to make a move, given a certain game state. Notice how the public makeMove method defines a universal algorithm for making a move, but the individual step of getting the move is delegated to an abstract method which you must implement in concrete subclasses. Such a design is known as the template method pattern in object-oriented programming. Making a move entails checking if it's the given player's turn and whether the move exists. The getMove method returns none to indicate that no more moves are possible, and the abstract player class uses the walrus operator to simplify the calling code. To make the game feel more natural, you can introduce a short delay for the computer player to wait before choosing their move. Otherwise, the computer would make its moves instantly, unlike a human player. You can define another, slightly more specific abstract base class to represent computer players. Computer player extends player by adding an additional member, delay seconds, to its instances, which is equal by default to 250 milliseconds. It also implements the getMove method to simulate a certain wait time, and then calls another abstract method specific to computer players. Having an abstract computer player data type enforces a uniform interface, which you can conveniently satisfy with a few lines of code. For example, you can implement a computer player picking moves at random in the way seen on screen. You use choice to pick a random element from a list of possible moves. If there are no more moves in the given game state, then you'll get an index error because of an empty list, so you catch it and return none instead. You now have two abstract base classes, player and computer player, as well as one concrete random computer player which you'll be able to use in your games. The only remaining element of the equation before you can put those classes into action is the abstract renderer, which you'll define next. Giving the tic-tac-toe grid a visual form is entirely up to the front end, so you'll only define an abstract interface in your library. This could have been implemented as a regular function because the renderer exposes only a single operation while getting the whole state through an argument. However, concrete subclasses may need to maintain an additional state, such as the application's window, so having a class may come in handy at some point. You now have the tic-tac-toe library with a robust domain model, an engine encapsulating the game rules, a mechanism to simulate moves, and even a concrete computer player. In the next section of the course, you'll combine all the pieces together and build a game front end, letting you finally see some action. Build a game front end for the console. So far, you've been working on an abstract tic-tac-toe game engine library, which provides the building blocks for the game. In this section, you'll bring it to life by coding a separate project that relies on this library. It's going to be a bare-bones game running in the text-based console. The most important aspect of any game front-end is providing visual feedback to the players through a graphical interface. Because you're constrained to the text-based console in this example, you'll take advantage of ANSI escape codes to control things such as text formatting and placement. Create the renderers module in your console front end, and then define a concrete class that extends the tic-tac-toe's abstract renderer in it. If you're using Visual Studio Code and it doesn't resolve the imports, try quitting and reopening the editor. As you can see on screen, this worked for me, allowing the imports to be resolved correctly. The console renderer class overrides render, the only abstract method responsible for visualizing the game's current state. In this case, you start by clearing the screen's content using a helper function, which you can define below the class. The string literal seen on screen represents a non-printable escape character which starts a special code sequence. The letter C that follows encodes the command to clear the screen. Note that the print function automatically ends the text with a new line character. To avoid adding an unnecessary blank line, you can disable this by setting the end argument. When there's a winner, you'll want to distinguish their winning marks with blinking text. You can define another helper function to encode blinking text using the relevant ANSI escape code. Here you wrap the supplied text with opening and closing ANSI escape codes using an F-string. To render the tic-tac-toe grid filled with players' marks, you'll format a multi-line template string and use the text wrap module to remove the indentation. The print solid function takes a sequence of cells and prints them with an additional gutter around the top left corner. It contains numbered rows and columns indexed by letters. The gutter will make it easier for the player to specify the coordinates of the target cell where they want to put their mark. While this basic display would work okay, improving this would be desirable. In the next section of the course, you'll take a look how to make a couple of improvements to make the game more visually appealing when a winner is declared. Visual improvements when the game ends. If there's a winner, you'll want to blink some of their cells and print a message stating who won the game. Otherwise, you'll print a solid grid of cells and optionally inform the players that there were no winners in the case of a tie. The console renderer class is now modified. Print solid is now removed and replaced with a conditional. Your messages contain special syntax for the name aliases of Unicode characters including emojis in order to make the output look more colourful and exciting. The example scene on screen will render the emoji scene on screen. Note that you call yet another helper function, print blinking, which you'll define next. This new function takes the sequence of cells and the numeric positions of those which should be rendered using blinking text. Then it makes a mutable copy of the cells, overwrites the specified cells with blinking ANSI escape codes, and delegates the rendering to print solid. At this point, you can test your custom renderer using 2 computer players built into the Tic-Tac-Toe library. Save the code seen on screen in a file named play.py located in the front ends folder. When you run this script, you'll see 2 artificial players making random moves, leading to different outcomes each time. While it's interesting to look at their gameplay, there's no interactivity whatsoever. You're going to change that in the next section of the course by letting human players decide what moves to make.